2 over exponential functions and graphs. An exponential function, you've probably seen graphs of them, and they grow up very, very quickly. The definition of that will be f of x, so that's our function notation. So f of x is equal to something a times to some power of x. So x will really be our variable. What we've always seen in the past is the other way around, x to some power. And that's not how it's going to be now. So first, we're just going to be graphing it. Some stipulations on what a has to be. A has to be positive. And that's because if we were doing negative numbers, we would end up with really gross things that would be like i's and stuff that we wouldn't know how to graph. And it also cannot equal 1. And that's just because 1 to any power, 1 to 500 would still equal 1. So if a was equal to 1, we would just have a straight graph just at a equals 1. So in order to plot something like this, we're going to have our axes. So I'm just going to leave them dotted because it really doesn't matter. And I'm just going to go ahead and place it down here. So what we're actually going to end up doing is basically making a table of values and making a whole lot of things. So if, for example, our function value was f of x equals 2 to the power of x, we're going to pick some different values of x. So 0, 1, and 2 are always good places to start. But we also need some negative ones as well. So let's do like -1, -2, -3. And we'll plot these points when we get done. And we'll see what we get out of them. When x equals 0, I have 2 to the 0. Anything to the 0 power is 1. 2 to the first power, anything to the first power is itself. 2 squared is 4. 2 to the -1, we have to use our powers. I didn't mean to make two tables here, sorry. We have to use our rules of exponents. So we basically put 1 in the denominator. 2 to the 1 is still 2, so that is 1/2. Okay, we're going to do the same thing for -2. 2 to the -2 means that I have 1 over 2 squared, which means I have 1 over 4. 2 cubed, or 2 to the -3, would be 1 over 2 cubed, which will be 1 over 8. And then I'm going to go ahead and plot these points on my axes. So 2 to the 0 power, so this is a x equals 0, so that's my y-axis. I have a function value of 1. So I go up 1 and plot that point. Most of the time it will cross right at 1, but that won't always happen depending on what else you have in your function. 2 to the first power is 2, so I go over 1 and go up 2. And then I go over 2 and I go up 4. So 2, 4. And I might actually do 3 down here as well so that I can see another point. 2 cubed is 8, so then I'm going to go over 3 for my input, and then I'm going to go up 8. 1, 2, 3. And you can kind of see that major growth right there. And if you look at my fractions here when I had negative exponents, all that I'm going to do is keep getting smaller and smaller fractions. But I'm never actually going to get anything that gets to 0 ever. So that's what happens with exponential functions, is it gets really, really close to 0, but it never actually hits it. So at -1, I had 1/2. At -2, I had 1/4. At -3, I had 1/8. And that's all that's going to happen, is it's going to get very, very, very close, but it's never going to cross this. It's going to keep getting smaller and smaller and smaller, but it will never actually cross. And this will, however, get very big very, very quickly. Some of your function values actually ask you to compute some of the things in a calculator. So if it had asked you maybe like find e to the 12th, e or 13, that looks like a 13. So what's going to happen is you're just going to get your calculator. Most calculators have an e on them somewhere unless you have a really, really basic calculator. So what I'm going to do is I'm going to go find my e, which is a little bit hard to see on this calculator, but it's just on top of your natural log button. So this is your ln button. We'll use that in a little bit, but not today. So we're going to do our second button and pick ln, and you can see it brings up e to some power. If yours did not bring up the little power piece, it's fine. It'll just bring up an arrow, and we'll still type in 13. And then it's going to give us some value. This is what e to the 13th is. This is what you would write down as your answer. It's just making sure you can find that e on your calculator. E is a really special number. You use it a lot in calculus. But you know how when we go to find a slope of a linear function, or even when we find these slopes of exponential functions, wherever I actually plug in my slope, it has the same slope as itself at that point, which is really weird and confusing to even talk about right now because we don't talk about a lot of slopes in algebra like we do in calculus. So that's just where you know where to find some of the things, and we'll go ahead and talk about some of the graph shifting that happens with exponential functions. And I had decided to draw them, but instead of drawing them, we're going to actually type in our functions into our graphing calculator. And it's fine, just go ahead and sketch the graphs as we do it. A few of them that we're going to do, I'm going to do 0.4x to the x, sorry. So I'm going to type in 0.4x, and then for my next one, I have 0.7 to the power of x. And then I have 0.25 to the power of x. And then I just want to look at what happens with these graphs. If I actually look at them, they look very much like they are all going to go through the same point, and they do. They all go through the point 0, 1. So if I look, I want to zoom in on these. And if I look at them a little bit closer, they all go through the point 0, 1 because anything to the 0 power is equal to 1. Any number to the 0 power is equal to 1. So what that means is that they all go through this common point. But if I notice that this is not exactly what the graphs looked like that we just did, so I'm just going to sketch them real fast. So they all went through 1. They kind of looked something along this line. I don't know which one is which. I'm not too worried about it, but they all went through right here. And if you notice the numbers that I put in 0.4 to the x, 0.7 to the x, and 0.25 to the x. Now I want to go ahead and plug in a few more. I'm going to go down, and I'm actually just going to type a couple different ones. And those different ones that I'm going to type in will be 4 to the power of x. And then let's do 2.5 to the power of x. And then 1.8 as well. And then let's look at these graphs. If I notice what these graphs are doing, is they're actually going the opposite direction. They are all going up, whereas these ones were all decreasing. So the ones that I typed in over here were were 4 to the x, 2.5 to the x, and 1.8 to the x. They still all went through the point 0, 1. And this was a very sloppy graph of mine. And they pretty much looked almost exactly opposite of those guys. So what actually happens is that if my A, so my A is my base, why we call it A, I don't know. If A is between 0 and 1, it's a decreasing. Can't spell decreasing. And if it is a is greater than 1, the function will be increasing. So I'm going to open a new page and look at some more types of graph shifting of the same function. We've already done f of x equals 2 to the power of x. So we'll just kind of play with this piece a little bit. Okay, we're going to talk a little bit about the graph shifting of f of x equals 2 to the x minus 2, and that's all in your exponents. So if you were to type that in one of the old calculators, it would look like 2 caret parenthesis x minus 2. If you have a newer calculator, it will actually make the little square box up here, and you'll just type in x minus 2. Okay, what this is going to do is it's going to shift the graph right 2 units. Okay, so this will be the 2 units. And so when it's minus in the exponent, it will be shifted right 2 units. So normally, f of x, 2 to the x, it would go through at 1, at 0, 0, and we're going to shift this point to the right 2 units. So I'm going to go through and I'm going to copy my old graph. So what this is going to do when I actually grab these points, everything is going to move over to the right 2 units. So instead of there, my points will be all over 2 units. So my original 0 was over here, and all that's done is gone over to the right. Everything else also gets shifted over just as much as it would have. So I redrew the original graph back on here, so I will try to pick a different color real fast to put those in. So this one is my original graph, and then everything else is just moved on a little bit. Okay, so then I'm going to move this original graph back over here. So my points were 0 or 1, 1/2, 1/4, 2, and 4. So that's what my original graph looked like. And then, well, maybe not quite like that. Definitely not like that. Okay, and then I want to give you another function. So let's say, for example, I have 2 to the x minus 4. Anytime the thing is not in the exponent with it, and it's just on the end, it's going to do it in the normal direction that we usually think about. So what that's going to do is move this down 4 units. So everything will come down 4 units. So I'm going to grab my graph. So this used to be at 1, so it's going to move down 4. So it's going to be 0, -1, -2, -3 is where my point will now go. All these points will come down with it. And, you know, like before, it wouldn't cross the y-axis, and now it's not going to cross the line -4. Okay, it's going to get very, very close to -4, but it will never touch -4. So this will move it down 4 units. Okay, basically the same thing if I had 2x plus 3 not in my exponent. Everything will go up 3. So if my original point was at 1, 2, 4, I'm just going to draw a few of those easy little points to graph. And then I'm going to go up 1, 2, 3. So this new point will be at 1, 2, 3. Everything else will get moved up 3. Okay, 1, 2, 3. All those points will also get moved up 3. And so now, instead of not crossing my 0 line, it's never going to cross my positive 3 line when I go through, and I kind of made a sloppy y equals 3 line, but it's never going to cross that line. So if it's not in the exponent, it will move it up or down, actually the sign that it says to do. And then, for example, if I had another one, if I had 2x, let's say, plus 5, 5 might be a little bit big for the graph that I have here, plus 1, in my exponent. So since a minus sign in the exponent moved it right, the plus sign will move it left 1 unit. I will actually make a 1. So if my original points were here, 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 everything is going to get moved left 1 unit. So I just jump everything over. And then I redraw my graph. And so I could have multiple graph shifting things all in the same thing. Some of the graphs, however, get really, really confusing, and it's easier to actually just take some new points and plot them than it is to actually learn all of the graph shiftings that happen with an exponential function. So if, for example, I have f of x equals 5 minus 0.5x to the x, sorry. There are a few things that I could definitely tell are going on. Since I have a negative in front of this piece of it, I know it's going to be upside down, excuse me, and I know it's going to be up 5. But really, this negative sign and the half, which is between 0 and 1, a lot of it just gets more confusing than anything else. So really, one of the easiest things to do is to just replot everything. So I'm going to pick some values for my x's. I'm going to go with stop. Okay, so some of the easiest things to always plug in will be like -3, -2, -1, 0, 1, 2, 3. And then I'm going to see what I'm actually going to get out of my function. So I'm going to use a calculator to evaluate some of these things. So, but I'll have 5 minus 0.5 to the -3. And that actually gives me -3, which is very odd. And then I'm going to plug in -2. So I have 5 minus 0.5 to the -2, which gives me the function value of +1. Then I'm going to plug in -1. So I have 5 minus 0.5 to the -1. And that gives me +3. Then I'm going to plug in 0. 5 minus 0.5 to the 0 power. Anything to the 0 power is automatically 1. So 5 minus 1 is 4. Then I'm going to plug in 5 minus 0.5 to the 1. So anything to the first power is itself. So 5 minus 0.5 is 4.5. 2, I'm going to plug in 2. So I have 5 minus 0.5 to the second power. 0.5 squared will be 0.25, so it will give you 4.75. Ah, my pen. And then I have 5 minus 0.5 cubed. 0.5 cubed is 1.25, which will give us 4.875. So I'm going to go ahead and possibly try to draw my line at 5. So that's at the top of my graph here. I'm going to draw a dotted line just so that I know that's basically where it's kind of like where my asymptote is. It's not necessarily an asymptote, but it will never cross it. Okay, then I'm going to go ahead and I'm going to plot these points. So at -3, 1, 2, 3, I was down 3. And then at -2, I was at +1. At -1, I was at +3. And at 0, I was at 4. At +1, I was at 4.5. At 2, I was at 4.75. At 3, I was at 4.875. So what's going to happen is this graph is going to get extremely, extremely close to 5. So I'm going to try to draw this, and I'm drawing with my mouse, so it might actually look better is what it's looking like. So this is what my graph's going to look like here. So if I kind of notice this negative sign, what it actually did was it flipped it across this line. So before, without, if it was a plus, it would have looked kind of like that. So this kind of flipped it from what my original generic graph would have looked like. 0.5 made it come from this direction, and the 5 in front here gave me this line. So it doesn't matter if I had wrote it as negative 0.5x plus 5. It's still going to give me the same graph. So don't think that just because the x piece came last that it's really going to change a lot. But the easiest way to go about doing this is really to plot some points, because there's so many different rules for exponential functions in graphing. And then we're going to do some stuff with compound interest. And I just spelled it out since I'm writing with my mouse. Okay, my formula for compound interest is A equals P for principal, and it is going to be 1 plus the rate of return that we had, so R over N. N is the number of times it's compounded per year, all to the power of nt. So N is the number of times it's compounded a year, T is the amount of time. I guess it's not necessarily amount in years, but the amount of time that it's done per time period, whatever it is that they gave you. A will be the amount of money that you will have after the principal is grown at this amount of time. So if we like to do lots of words, I like to use A for amount. I don't even know if that's actually what it stands for. P is principal. And it's principal, like your principal at the school. R is equal to, usually that's called like your APR. I'm just going to say your rate. N is the number of times that it's compounded per whatever your time period is. So the number of times it's compounded per time. That's all I'm going to write. And T is actually the amount of time. So an example is you're given $100,000, or maybe not you're given, you have $100,000. And that maybe, is that too much? Okay, so I have $100,000 and I'm investing that at 6.5% interest. And I want to write a function, and it also tells me that I'm compounding semi-annually. Semi-annually means twice a year. That's annually, just in case you were wondering. Semi-annually is N equals 2. So I have to figure out what my R and everything equals. Don't forget that when you're given a percentage, I need to change it back to a regular number. So it will be 0.065 is what I'm actually going to be putting in my formula. My P is the amount of money that I started with, which is 100,000. So we don't have to actually change those ones. Okay, when it tells you to find the function, I'm going to write A equals P, so 100,000. 1 plus R, so 0.065. So 0.065 over 2 to the 2t. That will be what my function looks like. That's all I'm asking you to write out when it asks you to find the function. However, they're going to ask you to find the amount after a certain amount of years. So find it for t equals 2, 4, and we'll say 10. Somebody's running a chainsaw out of my window. So to find the amount of money, I'm going to plug in 2, 4, and 10 separately into the equation a couple different times. And so I'm actually just going to use the calculator to plug that in. So when I do that, I'm going to clear everything out of here so that I can see it. I'm going to do 100,000 times 1 plus, I'm going to make my fraction, 0.065 over 2, and I make that fraction inside of my parentheses. And then I have two sets of parentheses here around it to represent these ones. To the power of, if your calculator does not automatically put it up in the little square box, you need to use parentheses. I could use parentheses just so you can still see what it would look like. I'm still going to use no longer a t, but I'm plugging in actually 2, so I'm going to do 2 times 2. I could just quickly put in a 4. Okay, I'm going to figure out the amount of money that I'd have, and this is the amount of money that you would actually gain. So the amount that I gain is 11364 and some change. You do need to write the change, but I'm not going to. That is the amount of money that I have gained. So that means after 2 years, the amount of money I actually have is $111,364. So if it asks you for the amount actually in the account, it's the 100,000 plus the amount that you gained in interest. Then let's go through and do it for 4 years. I'm going to just do second enter so that I can retype everything in. And the only thing I'm changing is where my t was, I'm plugging in a 4. So I still have the same exact equation if you guys want to see that. Okay, I now have 12,915 in interest, so 12,915. So that was the amount that I gained, and I have to add it back to my original amount. So that means I'm going to have $112,915 in the account. After 10 years, I'll go through and do the same thing real fast. So second entry, instead of 4, I'm going to write 10. I don't necessarily have to have that in parentheses. I would gain 18,958. So in the amount in the account, I add it back, I would have $118,958. If it asks you for the amount of interest that you gained, it would just be these top numbers. If it asks you for the amount in the account, you have to actually add that back in. That was my attempt at a comma right there. If it asks you to graph the function, this amount in front is our actual starting amount. So what I'm actually going to do is I'm going to scale this by like 50,000. I'm going to say 50,000. So then that would be 100,000 here at this line. And then that's 150. So my starting amount that I had at t equals 0 was $100,000. And then after 2 years, so that I can go out 1, 2, and I would have 111,000. After 4 years, I have 112,000. My graph is not exactly to scale. After 10 years, I have 118,000. That's not 10, so that's a bad stop. Over here, I might have 10, and I'll go up to 118,000. So money is something that grows pretty slowly. This is an awful graph that I'm doing with my mouse. I'm sorry about that. So I will have you guys do work on page 408. And I will have you do numbers 3 through 63 by 3s.